a film mainly about work, kinetic energy, potential energy, and how all those things constantly equal each other out, and some power. But before we go into that, I want to talk about the four fundamental forces in this universe. Our first one we've been talking about pretty well all year, and that's gravity, and that's because masses attract each other. Then we're also going to get into electromagnetic forces. These are both electrical forces and magnetic forces that act perpendicular at right angles to each other, and they're usually what hold molecules together. If I'm going too fast, feel free to stop this at any time. Strong nuclear forces are going to be what hold the nucleons together. Nucleons are protons and neutrons that are in the nucleus of an atom. And then we get finally into weak nuclear forces. So when you put it all together, you get strong, weak nuclear, electromagnetic, and gravity. So it spells SWAG, as in you need to get your swag on. And I sort of skipped over weak nuclear. Weak nuclear are what they hold the radioactive particles in the nucleus together. For instance, the gamma rays, the alpha rays, the beta particles basically hold electrons into the atom. So a lot weaker than the ones that hold the protons together. Now, Einstein and a few others came up with this thing called the GUT, or the grand unification theory. And what it says is that all four forces are actually one single unified form. They can simply change from one thing to another. And that's what we're going to bring us into this next law that we have called the law of conservation of energy, is that since forces make energy or do work, then we can always change from one form to the next. Energy is the ability to do work or produce change in an environment. So if I take a force and I go over a certain distance, I can do some work. But in order to do work, I'll be able to have to get the energy from within inside of me. I get energy from eating food and all that good stuff. So when I burn those calories, it allows me to use a force. And when I move that force over a certain distance, I've just done some work. So the second definition of work is changing the energy of an object using a force to move it a certain distance along the way. So the formula we're going to use for it is work equals force times distance. And then you have to multiply that by the cosine of theta. We'll talk about that way in just a little bit, because the distance has to be in the same direction as the force is. Now, both work and energy are both measured in a specific unit called a joule. So the units for energy and work are joules. Let me bring up here, we're going to do a practice problem real quick. So here's my practice problem. It says a player exerts a 4.5 Newton force on a 105-gram hockey puck over a distance of 0.15 meters. How much work was done? Well, the work equals force times distance times the cosine of theta, which we'll talk about more of that in a little bit. The force he put on it was 4.5 newtons. The distance he put on it was 0.15 meters. So you simply take that 4.5 and multiply it by the 0.15, and you end up getting 0.675. Remember how I said all work was measured in joules? Now, if you notice, I did not put in the cosine of theta, because since the force and the distance are going the same direction, in other words, the force is going like this. This is my force. The distance is also going straight across the ice like this. You see how there's a 0-degree angle between here? Well, the cosine of 0 degrees is 1. So therefore, I really don't have to put that in there. Now, the next thing it says, what is the change in the puck's energy? Well, if you remember, I said that work equals the change in kinetic energy. So therefore, if I had a 0.675 joule change in work, I also had a 0.675 joule change in kinetic energy. Let me go back here real quick. On the last notes, it gives you the how to do power. Now, power is how fast you do work, or the rate at which work is done. So I'm going to take the work and divide that by the time it takes to do it. Well, if you notice on this equation here, I put in the formula for work, force times distance times the cosine of theta, and divide it by the time. Now, what's the unit for power? No, I said, what is the unit for power? That's not a question, that's a statement. A watt is the unit for power. So let's come back here and do this little problem on the back side here. If I want to find the power of the hit, we're going to take power equals work divided by time. Well, we said the work was 0.675 joules, and we said that it took the person, I thought I had it on there. I did not do that, I'm sorry. I should have said that it took 0.1 seconds to do this. So he hits this in 0.1 seconds. I have to give you that time. So if I did this in 0.1 seconds, a joule per second gives me a watt. And so 0.675 divided by 0.1 equals 6.75 what? Watts. There you go. That's the power. Let's continue taking notes back on the other side now. And once again, the work energy theorem simply says that the net work, or the work done on an object, has to equal a change in kinetic energy. So once again, that's what they call it. That's not work minus energy, that's just work energy theorem right there. And it's all one thing. Well, let's talk about kinetic energy. Kinetic energy is energy due to motion. And it says that KE equals 1/2 mv squared. Or you could say that kids eat 1/2 of most of their vegetables in a square meal. So if you double the mass, you have twice as much mass, you're going to have twice as much kinetic energy. But if you double velocity, you're going to have 4 times as much kinetic energy. So let's do a practice problem with kinetic energy here. I'm going to go back to this one. Uh-oh, I have a potential energy problem here. I want to do a kinetic energy problem. Let's come down at the very, very bottom, number 3, where it gives you the roller coaster problem. Okay. And on the roller coaster problem, it says a 1,000 kilogram roller coaster is moving at 26 meters per second. What is the kinetic energy? Well, I'm going to take KE equals 1/2 mv squared. So KE equals 0.5 mv squared. I'm going to put in the mass, which is 1,000. I'm going to put in the velocity, which is 26. Don't forget that it's squared. So if you square 26, you take it, multiply by 1,000, and you take half of that, you end up getting 338,000. And the units for it is joules. 338,000 joules. So that's how you do kinetic energy. Let's go back and we'll look at some potential energy here. Potential energy, whoops, I just went the wrong way, sorry about that. Potential energy is the energy you have due to your position. So in other words, if you're up on a diving board, you have a potential to fall off. So an object raised off the ground has potential energy to do work, and that is what we call gravitational potential energy. Now, what we're also going to notice is that when you change potential energy, you have to do work. So work is negative potential energy. Let's think about this. You have potential energy at the top of a diving board. When you fell off that diving board, at the very, very bottom, you'd be able to do some work on somebody. You could flatten them. Well, you would have lost all that potential energy. So that's why the negative potential energy change is equal to the work done on something. So when you look at potential energy, springs have elastic potential energy, electrons have electrical potential energy, a diver has gravitational potential energy. So we're going to do a new formula here of potential energy is mass times gravity times height, or PE equals mgh. So I remember this as physical education makes guys or girls, whichever one, healthy. PE equals mgh. So let's do a practice problem with this one. I need to go backwards here. And I'm going to do this practice problem where I have a 0.18 kilogram ball falls 250 centimeters. How much potential energy does it have? Well, we're going to start off with PE equals mgh. I'm going to plug in my mass of 0.18. My gravity is 9.8. And my height is 250 centimeters. Remember, you got to divide this by 100 because you cannot use centimeters in a formula. So that gives me 0.25 meters. 0.25 meters. And so when you multiply the 0.18 times the 9.8 times the 0.25, you end up getting 0.441. And remember, all energy and work is measured in joules, or J's. That says how much work is done. Well, work is negative change in potential energy. So at the very, very bottom, the ball had no potential energy. So the negative change in potential energy here, it's negative delta PE equals the work done. So my negative 0.441 joules is also the change in work, or the amount of work that was done on the system. Okay. All right, let me go forward here, and we'll finish this up. We're also going to look at springs and figure out how much elastic potential energy is a spring. We'll do this a little bit later. I just want you to write down the notes. If you notice, the elastic potential energy of a spring, though, sort of looks like the formula for kinetic energy. Remember, kinetic energy was 1/2 mv squared, and this is 1/2 kx squared. So once again, all those forces, all those energies look like they have the same formulas, and so they probably come from the same internal force somewhere. This weird K that we got here, that's going to be different for every spring. And the higher that K is, the stiffer the spring is going to be. Once again, we're going to do a whole lab on what we call Hooke's constant, or Hooke's law, that says that force is proportional to the stretch. So if I put more force on a spring, it's going to stretch more. So F ends up equaling the Hooke's constant, or the spring constant, times X, which is equal to the stretch. So F is force, K is Hooke's constant, X is stretch. Now, don't forget that elastic potential energy is going to be the same thing as regular potential energy. We could say that an object that has the potential to do work, but it has not done it yet, so the potential energy belongs to the system, is not on a single object. It's on the whole system here. So let's talk about conservative forces versus non-conservative forces. Conservative forces are forces for which the work done does not depend on the path. For instance, gravity. It goes up and down, right? So it doesn't really depend on the path taken. So if I climbed a ladder straight up 10 meters, I would have the same potential energy at the very, very top as if I went up a long ramp and still went up 10 meters. So as long as I'm up at the, 10 meters up, I still have the same potential energy. Now, non-conservative forces like friction, that depends on what path you take. So if you fall straight down off a diving board, you have one bit of friction, like air resistance. But if I went down a sliding board, I would have more friction because I'm going a longer distance. And plus, I'm not in the air, I'm rubbing my tail in against metal. So friction is a non-conservative force. Gravity and things like that are conservative forces. And so the potential energy can be defined only for conservative forces. So you don't get potential from friction. So once again, to sum all of this up, we have what we call now the extended work energy theorem. The fact that the work is the sum of all the works of the conservative forces and things like friction. So you have to do the network on both of them is both conservative forces and friction. The law of conservation of energy says that energy cannot be created or destroyed. And that's why potential energy, the change in potential energy is going to equal the change in kinetic energy. The work that you do something is going to give something kinetic energy. If you lose potential energy, you've done work, which also gives it kinetic energy. All these things are constantly equal to each other. So therefore, I can come down here at the very, 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 very bottom. You'll see where I have that work of conservative forces equals the change in kinetic energy, which then equals the negative change in potential energy. So this is that work energy theorem that I want you to know about. Now, if you have the work of non-conservative forces, you have to add both the kinetic and the potential energy together. Because once again, it depends on the path you take. So when you lose potential energy, you're going to gain some kinetic energy, but not always the full amount when you have friction. Okay. Hopefully that helps. Got all those written down. We'll do some labs to make some sense out of this stuff, and hope to see you soon. Thanks. Bye.